Good afternoon and welcome to this webinar from VTech Energy. Today's topic is how to optimize your district heating grid by using NetSim grid calculations. So my name is Johan Helén and I'm your webinar host for today. I'm also the VP of Sales and Marketing here at VTech. So if you have any questions afterwards, feel free to email me at my email address that you see on the screen. I also have my colleague Gustav Edlund with me from Stockholm. He will be the webinar presenter today. So this is a two-part webinar. First we will start off and explain a little bit about how the system is set up, and then Gustav will show you what the system looks like and how you can create different types of simulations in order to help your grid. If you have any questions during the webinar, feel free to type them into your application that you will find in your right-hand corner. We will then, in the end of the webinar, address as many of the questions as we can. If you would like to try NetSim with your own grid data, that is something that is possible. So in that case, please contact us at sales.energy@vtech.se. First, let's start with some key points on what NetSim is and what it can do. So NetSim is a very easy to use software that can make static or dynamic simulations. The simulation model that we use is quite powerful, so you can both use it for big grids or dynamic simulations and still have a very good result, a very accurate simulation. It handles both heating and cooling grids, so if you have one or the other or both, that's not a problem for the system. It accepts multiple production plants also, and if you use a system like NetSim right, it will reduce the number of consultancy hours that you need in order to keep your grid optimized, and it will also decrease pump costs. Let's have a look at the NetSim system overview here. So we have the NetSim Oracle database that you see in the middle of the screen. And on the left-hand side, we have the data that we need in order to make a model, meaning a virtual grid that you can make calculations on. So that's network data, consumption data, and background maps. And we will get back to what type of data these different topics have under them. So we put that information into the NetSim Oracle database, and as you can see, you can access that from your client computer with NetSim, and you can also make changes in the model. So you can say that NetSim is two different modules, one for maintaining the model, and that means that you could add a customer or change a pump setting or something like that, and one part is the analyze part when you have done a simulation. And as you can see, we have the simulation data from the Oracle database into the model, and then we will have an output file that you can view. And that's a file that you store for as long as you like, so you can have different scenarios that you already have made simulations for that you can bring up after 6 months or whenever you like. Let's have a closer look at the data that is needed in order to make a model. And we will start with the network data. There are many different file formats. We mentioned a few of them in this presentation. So ESRI or SOSI could be two of those. If you have something else, then we will have to have a look at that format and see how we can extract the data. When we talk about the pipes, what we need is the start and ending coordinates, X, Y, Z. And if you have the coordinates between the start and the end. So if there are any bends, we would like to know about that as well in order to make the best model. We need a diameter of the pipe, the internal diameter. We need to know what material the pipe is, what type of insulation, thickness, and we need also to know if it's a supply or a return pipe that we are talking about. For the nodes, meaning the end points of the pipe, we need the coordinates. We need the Z coordinate if you have that as well. And consumer data, we need to know what node it is, and we need to have a facility ID. And when we talk about consumption data, that often comes from some kind of billing system, and we would like to have that in a CSV file if possible, and that should contain things like facility ID, nominal power demand in kilowatts, energy consumption in megawatt hours per year, average cooling, for example, and what consumer type, if it's a residential or a industry, for example. And then we have the background maps, and there are many different formats. DWG and DXF are a few of those that we support. So that's one of the things that you can do in order to make your model a little bit more understandable, is to have a background map. Today, NetSim is used by many companies from Norway to Qatar, and it's a quite big mix between large and small corporation and utilities, which means that even if you do not have a big staff, NetSim is a tool that you can use. So even small corporations use this software. We have ready-made connections to many GIS systems, which means that installing the software is quite easy, and that's something that we do from our part. NetSim is a proven system. It has been on the market for quite some time. We are the market-leading choice for both district heating and district cooling grids. If you would like to get in contact with us, you can do so by email or telephone. Email us at sales.energy@vitec.se if you have any questions. And with that said, we will go into part 2, and this is where Gustav will take over and show you what the system looks like and how you can optimize your grid by using the calculations from NetSim. So thank you very much, and welcome, Gustav.
Good afternoon, everybody. The agenda, we are going to look into the model data itself in NetSim, take a quick view through the Analyze tool, and how to configure static simulations, how to maintain a model, also configure and perform simple dynamic simulation, and if we have time enough to also look at the pumping in the model. Don't forget or remember that you can put questions in the application and during this session, or mail it to us if you have anyone. So here is my screen. Yes, over here. So this is the model interface. Modeling interface in NetSim, where we have some simple background maps added. It's facilities and streets loaded, and over here we have, in the blue, we have the pipes and nodes. Modeling data. Look into if we look into a pipe, we have the pipe diameter. Let me mark this pipe over here. We have the pipe type or pipe dimension. This is a description of the actual pipe in this line. So let's have a look at the pipe description. It's like this. Okay, this is a copper Swedish manufacturer, and we have of course we have the internal diameter, roughness of this pipe, and the heat loss coefficient. This is what the main data we need for the actual calculations. And of course we can have put in more data about this pipe type, for instance price category or something like that, and if it could be used for when you are making dimensioning of the pipes. Let's close that one. So the pipe has a starting node and an ending node, and if you look at the node over here, we have the name of a node, of course, and the elevation of this node and coordinates of node. If it is a consumer like this one, we also have defined in node data power demand and actual return temperature from this substation. Instead of power and return temperature, we can use flow and cooling if they are the known values. When taking data from a GIS system, we then we get a lot of nodes. There's often for a T or something or bend, there is at least a couple of nodes, maybe 3 or 4, and very short pipes between them. And this isn't actually very good for the calculation. You have a lot of fuss in the calculation. Therefore, we have tools in NetSim to maintain or trim the model. Let's look at one tool over here. It looks at trim model. We can put in a length. So any pipe shorter than this length, if possible, can be added to the pipe. It's a pipe nearby or connected to the same nodes. So let's have a look for this example. That if I run this through, I will remove 40 pipes in this model and make another 40 pipes somewhat longer than before. Very often, sorry, I got it wrong, but that's okay. Very often, when we take a large model input, we can take away something like 10 or 15% of all the nodes in the model. This is a very simple or very small network we're looking at, so it's very easy to make calculations on this. So let's make a calculation. We go over here to the calculation window, and we have the load case defined as for the load at -15 degrees outdoor temperature, and any global factors there are put to 1. The heat losses are calculated against the environmental temperature of 3 degrees in general. So here it is. Let's make a calculation. Okay, I put in the path also. Let's call it -15, like that, and calculate. We start calculation, and it's done. So now the results are visible in the Analyze tool. So let's have a look at the calculation results. We have the map window where we can define what kind of parameter we want to show. If I, for instance, take pressure difference like this, we have a maximum value of 480 kilopascals in a network and a minimum value of 20. So let's have a look where this is. So we set the upper limit to 400 and lower limit 100, and put on apply, and there we have colors telling us what the results in each pipe, in what level they have. So we can, if we look into the low areas with low pressures, over here we have fairly low differential pressure. It's something like 19 kilopascals. Actually, it don't work very well over here. In the case we have the loops in a network, maybe a flow direction is interesting. So let's look over here. I like the flow arrows, and there is a flow direction in a supply line. And if we want to take return line, we mark that one and apply, and the arrows, they are going the other way. But I've seen cases when supply and return line, they have the same direction, that's for sure. Other kind of plots. You can make a profile through a network. Let's start over here. and add this node as starting node for the profile. And then we go to the next stop. It should be at the plant over there. And let's go over here with the low pressure over there. So now we have a path through the network starting over there, passing the plant, and ending over there. Let's look at the chart. There we have pressure in meter water column. We can use kilopascal, of course. And if we want to look at the cavitational pressure, we are well above that. And if we have construction limits, for instance 16 bars, put in a legend and the value and plot like that, so we have 16 bars over here. That was the pressure. If we look at the pressure level instead, more convenient, we have this picture. So over here is the starting node, over here we have the plant, and all the way over there we have the last substation in that part of the network. Of course, we can look at, instead of the pressure, we can look, for instance, at the pressure gradient. And then, of course, we close this one. And as you can see, we have fairly high pressure gradients in these pipes over there. It's bar per kilometers compared to the general value in the network. So that is a narrow section in the network. Temperature, plotting that, we have supply temperature in the red over here and return temperature over there. And as you can see, we have the temperature drop in the endings of the network where the flow is small. Looking at the map once again, if you want to look, for instance, after a node with or a pipe with the highest velocity, you can sort over here, and that one should be at PC1. We have the showing map. Okay, there it is. That's a pipe with very high velocity. Now, as you can see, the pipes are very wide and bright. So let's make them some tinier, like that. Apply, and let's clear the route. So we'll get rid of the blue one. And here, over here, we have that pipe we're looking for. All data in this grid you can just copy and paste into Excel, and you can make your own calculations on heat losses or something like that. This tool is very simple to use. You can very fast get hang of where are my trouble spots in the network, and the simulation is already done. So there is no risk that you destroy a simulation or file with this tool. Actually, when I used to say, if you're going to a meeting and you want to present the results for a certain project or something like that, if you have made the calculations, then you can just put the map up on the screen and walk it through, and you have all the answers on the screen. And of course, if you want to present values from a certain nodes in a plot, you can light up labels like this, where you decide what values should be shown in the labels for nodes and pumps. Pipes. So that was the simulation analysis. So let's make another kind of simulation. Let's make adding pipes, editing the model. So I go to, I take this one. Actually, it's the same model, but it's a copy of the model. You can add the background map like this. Load background. I use this one. It's just a simple DVG files that we have. So here we have some pipes. Maybe I have done a sketch plan which houses to connect. So we can have also them in a background map like this. Open up like that, and here we have some pipes. So let's make a new pipe. Draw pipe, it's a command. When take the cursor to a node, and when the node hits, you have connect, and then you just click where the pipes are going, like that. And the ending node, we have the set level, the elevation from the nearest node in the model, and if it's okay, we can use it. Otherwise, we can perhaps change the level, like that. Save and close. And the pipe over here, we are going to let NetSim decide the dimension, so we take this one. And here's the pipe. And let's take another pipe over here, service pipe, draw pipe over there, and we have the ending node. Power demand to 80 kilowatts, and return temperature 50 degrees. Save and close, and here's the pipe. Save and close. So it's fairly simple to draw pipes. Just point and click. Now let's go to the calculation. At this point, we have in this configuration we have defined that if the pipe will be less than 100 millimeters internal diameter, then choose a pipe that will give a maximum 1 meter per second velocity. Otherwise, take a pipe that will give 100 pascals per meter as pressure loss. And let's go for calculation. There it is. And let's open the results. Over here we are. Now I have pressure difference as parameter, and over here we have something like we are in the between 100 and 200 kilopascals. Looking at the node, we will have 179 kilopascals as differential pressure. So that's okay. And the diameter 43 millimeters and should be the same over there. And over here we have 54 internal diameter. So for this reason, when it's just pipes with no loops, there is no, very simple to decide what diameter should be used. Another kind of calculation is dynamic calculation. And if I choose to over here and choose to the model, I use the decide for that one. It should be this one. To start with, we have the load the general load case for this at this point is for minus 15 degrees. Let's have a look at what data we put in, like that. Typical simulation cases when we're running dynamic simulations is to define the time constants. What time will it take for the water from the plant to reach the most far places in a network? For instance, if we have shortage of power, maybe we have consumers that can reduce their power consumption in special cases in a simple way. Starting and stopping of production plants, how will it affect the differential pressures in the network and so on? If we want to accumulate power in the network, at what time should I start a plant or rise the temperature to have the hot water at the substations when in the morning? Dimensioning of accumulators. Well, if the accumulator is located in the middle of town and you have plants in the suburbs, maybe you can get some information from this kind of simulations. Malfunctions, if you're losing temperature in a plant, what will happen? What way will what water travels to the network? That's that kind of simulations. So in this example, we will make this test. And we are starting with an initial load of something like 40 megawatts in the network, and we have losses about 1 megawatt. And if we look at the consumption, it will fluctuate during the day in a very normal pattern like this. For that, in the morning we have well beyond 50 megawatts, and also in the evening we have a peak, and here somewhere we have something else. So this we can simulate by putting in load factors for each hour and to manipulate the load in the network. To see to see the temperature front, or to see how the water is traveling, we are putting in just a short pulse of hotter water from the plant. And in this case, we are doing that at 5 o'clock it starts. So let's make the calculation. Looking at this plant over here, PC1, the node type is 1, and this is handled over here in our time series. So look at the time series from node type 1. Then we have a supply temperature rise at 50 minutes past 5 in the morning. We have 110 degrees, so we have risen to 12 degrees from the initial value. And it will stay for 15 minutes like that. And over here we have the load factor for the consumers. So let's make the calculation. Path, we put it over there. Yes, and start. And now we are going to pick up our time series file. We're starting simulation at 4 o'clock in the morning, using 5 minutes as time step and something like 37 time steps. That should get us to 3 hours, 7 o'clock in the morning. Let's start. And now the results in each node, each pipe is also input in the next calculation. and the factors are just manipulating the power in a network. It's done, and we are going to open Analyze. Now I want to look at temperatures, so we're going to show temperature, and the limits are 105. That means when the temperature higher 105 degrees, we are having a red color, and when it's below 98, we are in the blue color. Let's put in a legend like that. I think we could close the nodes. It's a cleaner map like that, and make them somewhat like that. So here it is. We have temperatures 98 degrees or less. 4 o'clock in the morning, and let's generate the slideshow. Over here, create animation. And now you can see we are putting in the water, and that's done. Let's have a look at slideshow. Over here, you can down in the south, you can see how it works in the loops, that we're feeding the loops from different ways, and we have that hot water is emerging out over here, and there it is also, and let's go all the way down. So something like 7 o'clock, then we have more than 105 degrees in the most distant part of the network. So in this case, when in the winter time, minus 15 degrees, 3 hours is an approximate value to get water all the way through the network. In summertime, much longer time. We can also look at the results by taking a path through network, a route. So I pick this one, pick this node over here, add node like that, and let's pass through the plant. See it over there, and let's go over there. Actually, I want to see what happens in the loop over there, so I do another route. A clear route. I start here in the south. I take that one. I go over here. I take this node, and now I'm in the loop. And let's go that way. Now I can go to the plant. And up in the southern paths, like that. And I take the chart and looking at temperature, like that. This is 4 o'clock in the morning. We have the supply temperature over here, down in the south and up in the north, and return temperatures, of course. And they are varying with the different substations, return temperature. So let's go step on. Okay, here you can see we have the temperature from the plant is coming here. And We're going all the way up to 110 degrees, and the water is moving in the different directions from the plant. And now we are something like 6:30, and as we can see, we have got some hotter water here, so the water is there, of course. And over here we can see what happens in the loop in the network. And fairly easily to create a simulation like this. In NetSim. Now let's have a look at pumping. If you remember, we had very low differential pressures over here, and that's because the pumping in the plant is regulated or has a set point in this node over there in the north. So let's add pumping over here. I want to have it in this pipe. So I mark the pipe, I go to the pump grid over here and add a pump. Create new. We can have a name on it, P34, like that. It should be located in this pipe, so I click on that, and there we have the pipe. It should be located in that end of the pipe, so I choose this node. It's located in the supply pipe. There we are pumping. We need a node for the set point, differential pressure, so I can mark this node. There it is, and pick the node. We have differential pressure as parameter, and we will have nothing less than 200 kilopascal in that. There it is. The load case, over here, calculation. The load case is for -15, but let's change it to -20 instead. Level 1 return temperature, and update save before, and then update nodes. Like that. And now we took it at -20. And calculate. Closing and opening the results. I will make a profile, pressure profile, to see how it works. So add nodes, starting in the plant and pointing out over here. So we are passing in the pump, and if we look at the chart and look for pressure, we can see the pump working here. We can also look at the pressure level, for instance, and there it is. So here's the pumping. And of course, if you want to put in a pump design, you define the characteristic for the pump at a certain rotation, and you put in different pump lift and power demand for in the characteristica and connect it to the pump. Then you will have the pump efficiency and power demand for the pump defined also. Fairly simple. Look at the map, look at the differential pressure and apply. At this point, the lowest is 76. It should be somewhere here down in the south. Yes, and over here we have, as defined, 200 kilopascals. If you have any questions, you can put them in the application to us. Of course, sorry. This is a very simple net, or a smaller net, I should say. If we go to something more heavy, we can go into this net. I will take a map as background to get the measurements. Like that. This network has a more normal amount of nodes and pipes. For NetSim, something like 9,000 nodes and about the same amount of pipes. So there it is. Over here we have Stockholm City, and over here we have Södertälje, where they make the Scania trucks and so on. And over here we have plant. We have a plant over there, and this is just for pressure control. And over here we have the connection to the Stockholm City. This plant is just for backup reasons, but we have a lot of pumping in this network. In general, many calculations, you can just look at the main pipes in the system, and so we have a tool to divide the network in different levels. So take a look over here. All the blue pipes, that is service pipes in a model, and the green one is the distribution pipes, and the cyan, I think it's called, turquoise, maybe, that is the main distribution pipes in a network. Loops and so on, they are all in that network. So if you want to make calculation how to distribute water, what pressure we have in certain districts, then we can use the calculation on that level also. So let's have a look how it performs. With calculation, we are calculating on the third level, the main pipes, and we have put all the consumption from consumers to the third level. And just make a calculation. Starting it up. It's done. Let's have a look in the results. Like that. And now we are looking at pressure difference. We could take a profile to the network. So we start over here in this plant. And let's go through this plant over here. And then we make a turn and going all the way south on the eastern side and take this one over there. It's fairly easy to create a route. It's very fast. Look at the chart. Now we're looking at pressure. Very hard to see something. Look at pressure level instead. So here it is, the pumping. We can look at cavitational pressures and see that's okay in that way. And if we take a construction limit like 16 bars, put in a value, and show where it is. So as you can see, we have a lot of pumping, and the pumping is both in supply and return line because to hold the total pressure down. It's more secure. Also, if you lose a pump, it will not give that high pressure water hammer effects in a network. Before a pumping station, very often we have negative differential pressure. We cannot connect any consumers in that area, but that's okay. It's distribution line. And over here we have the final pumping in this area. And over here, well, they are nearly at the limit of what's possible to distribute with that configuration of pumping. So here it is. I think that's about what I'm going to show you. I have a couple of slides if you have questions about how to manipulate the consumers and get that kind of data into NetSim. Otherwise, we could look at any questions.
Okay, thank you very much for that presentation, Gustav. We have quite a few questions here, but I see that we have 12 minutes left, so there's time for more, I hope. If you have any questions, type them in right now into your application. It's very easy. You will find it in your right-hand side. Okay, so the first question here, Gustav, is quite fast one. Can you have background maps in NetSim Analyze as well?
Yes.
Yes.
It's
okay.
the same map.
So it's the same map for both the tool for maintaining the model and also for the Analyze tool.
Yes.
Okay. Next question is from Sarah. It was hard to see the production icon. Can I make it bigger?
Yes. The production icon is they are configurable over here. So if I go over here to options and make it larger, plants, no, 25.
So basically you can scale it from the picture.
Yeah.
Okay. Great.
Should be that big like right now.
Great. I hope you're happy with that, Sarah. Next one is from Mike. Is the Z coordinate absolutely necessary? We only have a few documents, and then with the Z coordinates is the elevation.
Now, the Z coordinate, it's an option. If you want to read the correct pressure in each node, then you need the elevation value in that node. You definitely should have it in the pressure control node at where the plant is. Otherwise, you don't need it. Differential pressure that drives the network around doesn't need the elevation to get the correct values.
Okay. But in the end, what we're saying is that if you have it, we would like to implement it, and even though it's just a few data points, like in Mike's case here. Okay, great. Okay, next one is from Marcus. You said that the system works for district cooling as well. How do you make the switch between heating and cooling?
In the calculation window, we have these switches over here. If I press cooling, now the model you should give a colder water in the plant than you get from the consumers, and it adapts some physical data on water also to the cooler side. So that's all that's needed. Sometimes you also have a single pipe, just not in the same model, but as you have both supply and return. But if you have a system with just transportation of water from one point to another, it's cooling, for instance, taking seawater and cooling and let it out somewhere else. You press this only supply, and now there's only the supply line is calculated in a simulation.
Okay.
Yeah.
Great.
So that's very simple.
Okay, thank you very much for that. Next question is quite heads-on. It's from Peter. How do you save money by using NetSim? Could you make some examples from your consultancy background,
yeah.
Gustav?
In any case, when you have a network, it's 10, 15, 20, 30, 40 years old. Then you have to make renewals in a network. They are building new streets. They are moving streets, moving houses. You have to move the pipes. And in that cases, you can always make the best of the situation. What is the demand nowadays? The original pipe was made from a general master plan made maybe for 50 years ago, and now there is some other buildings in the area, industrial. They have moved to China or something like that, so you don't have the demand. Then maybe you can reduce the size, or maybe you should hold the size up. That's a lot of money you can save if you use, for instance, normal with 250 instead of normal with 350. Or 100, for instance. Maybe you can use a twin insulated pipe instead of the single pipes.
Okay, great.
Do
you have any more cases that you have found?
If you want to renew something in the model, maybe you must shut down your main plant during the summertime to refine the heat exchangers or something like that, and you have to use alternative production. Then maybe you can, by altering your network, you can use the plants or production that is the cheapest one during summertime. I remember a case many years ago in a Swedish town where they had what's called heat pump that the operation person say we can't run it because we have not enough water when we are closing down the main pipe. But we said let's make a try, and then we made the closings and in the network and directed the water on other ways through the network and got the water to the I got the name. Got the water to the what's the name of heat pump? Okay, through the heat pump, and that summer they saved something like 1 million just by running NetSim a day.
Great.
So there's a lot of opportunities to save money by using a network or a grid calculation system.
Thank you very much for that. Next one is from Sarah. Are there any limitations to the diagram track when you set it? And then I guess that she means the plotting of the road that you need to make for a diagram.
No.
Are there any limitations to that?
No, we have the values we can plot: pressure gradient, temperatures, and you can go through all the nodes if you want to have it in diagram. It's very simple.
Great, thank you. Next question here, I can't see who is from, but the question is the software able to calculate costs, meaning savings of system operations, heat loss, pumping cost, etc. So can you put money on the megawatt hours?
Yes, it can. In the plant, we can, if we look at the plant we have over here, this plant, for instance, if you, come on, here it is. What is the cost for pumping in this station? What is the cost of production for per kilowatt energy cost? Any other taxes you may have? Cost you can define, and this can be done for any plant. And if you have a pump, or we can just choose a pump over here. That should be that one, yes, and save that. If we look at the pumping, where are they? Pump types over here. Let's look at that one. We define the pumping efficiency and what is the power cost for the pump per kilowatt hours, and then you can calculate what is the cost. Heat losses, of course, they are also calculated and could be transferred to a cost.
Okay, great. So you can get that in a report in the end when you have hit the numbers. Great. Next question is from Robert. Can the software analyze additional low temperature subnetworks for low energy buildings which use the return district heating water? Have you tested it on such a case is the question from Robert.
Well, we have made yes, we have made calculations and models when we're using return water and putting it as supply water to an area in the network. So that is possible to do.
Okay, great, thank you. Let's see, I think we have the last question here. What use do you have for NetSim if you do not longer build anything in your grid? The examples that we took earlier regarding the savings were more when you make some big changes in the grid, but if you have a quite static network, how can you use NetSim?
Well, you get a very good knowledge of your network. If the network size is of some magnitude, then you can, during the calculation, you can see where are the weak spots in my network, where do I have high velocities. If I want to, maybe I can earn some money by reducing pumping or something like that, just by switching out a very short pipe in the network. So you can still make savings, and I guess you can sleep very well, sleep better on nights, also when you get the grip of how the network is working. So even if there's no new buildings connected to the network itself is getting older each year, and all the weak spots, they are there, and the new weak spots are coming.
Okay, great. Thank you very much for that. We are out of time, so I would like to say thank you to you, Gustav, for the presentation. If you would like to get in contact with us, if you have any more questions or would like pricing information or information about having a trial with your own data, please feel free to email us at sales.energy@vitec.se. So thank you very much for tuning in, and have a nice day.